Welcome back, students. So, in the previous class, we have discussed about the basic ideas or the basic concepts behind how to make utilize of the timer module that is available in our 8051 microcontroller. In today's session, we will be discussing about the details about interrupts. Okay, so we know that the 8051 microcontroller supports three internal interrupts and two external interrupts. A total of five interrupts is been supported basically by the 8051 microcontroller. So we will be looking into the peculiarities or the features of each of these interrupts and how they can be used in our applications. So in the discussion will be regarding the special function registers and the properties or the principles or the concepts behind how the controller will be treating an interrupt that occurs in case of our 8051 microcontroller. Okay. So, if you look to the basic concept of interrupt, an interrupt is nothing but an occurrence of an internal or external event that interrupts the microcontroller to provide service of any device. Okay, that means the microcontroller will be doing a particular process, or it will be performing a specific task currently, and on the occurrence of this internal and external event, the microcontroller is forced to complete the current task, and irrespective, or rather than going to the corresponding or the consecutive location, it will be asked to divert to another set of instructions, execution of another set of instructions, so that it is going to service the request that is being produced by an internal device or an external device. Okay, so in case of an external event, so if this interrupt is being generated by an external device or an external event, then we can see that the status of a microprocessor or a microcontroller pin is been altered. This value, okay, if it is initially logic 0, on occurrence of this external event or external interrupt, the value will be changed into logic 1, okay, or vice versa, etc. But in case of the internal interrupts, okay, if this request is being generated by an internal event, like in case of 8051 microcontroller, the internal events that results in interrupt generation are timers and the serial port or the UART. So they won't be indicating any status change in the pin status. Rather, there will be some change in the values of the bits of some of the special function registers. Okay, so if you look to the if you go back to the previous class discussions, we can see that when the timer overflow occurs, the timer overflow flag, that is TF0 or TF1, will be set. Okay, so only this change is being indicated to the microcontroller to indicate the microcontroller that an internal interrupt has been occurred. Okay, but in case of an external interrupt, you can see that the logic level that is available in one of the pins of this microcontroller will be changed. Okay, now what does the microcontroller performs on occurrence of this internal or external event? So on receiving an interrupt signal, the microcontroller will be interrupting the execution of the main program. That means it will be completing the current instruction that is being executed, but it won't be going to the next instruction. Okay, so at that time, after completing the current instruction, the program counter will be having the address of the next instruction, so that value of the program counter will be stored or saved into a stack memory, and the program counter will be loaded with a new address which is necessary to necessary for servicing, okay, for servicing or solving the request that is been received to the microcontroller through the interrupt. Okay, so that memory location which has to be accessed by the controller in order to service this request is normally known as the vector address corresponding to an interrupt. Okay, and this procedure of routing the microcontroller's program execution flow from the current location to the vector address corresponding to an interrupt, and after completing this particular process, the stack program counter will be loaded with the value that we have stored in the stack pointer. Okay, so this ended process is known as interrupt service routine. Okay, so in general, where this location to which the control is being transferred on occurrence of an interrupt, that is the memory location to which the microcontroller has to go in order to uh, service the interrupt request is known as the vector address. Okay, so if for each of the interrupts that is supported by a microcontroller or a microprocessor, if we have such specific addresses which has to be visited by the microcontroller in order to service that particular request, interrupt request, we call that particular controller, microcontroller or microprocessor, possess a vectored interrupt structure. That is for each and every. So in case of this 8051 microcontroller which we are now studying, we have 5 different interrupt sources as in the basic format. Okay, so for each of these 5 interrupt sources we have specific addresses which has to be visited in order to address that particular interrupt request. So we call that, we say that the 8051 microcontroller possesses a vectored interrupt structure. Okay. Once this interrupt has been serviced, the processor or the controller will be retaining the uh, original program address or the original memory address to which the execution has to be resumed. Okay, so that is mean it will be fetching from the stack memory. So if you look to this particular block diagram here, you can see that for interrupt 1, okay, there is an external interrupt 1, and corresponding to external interrupt 1 we have an address location that is 0013h that is been mapped. Okay, so the controller is been executing some main program currently, and when an interrupt 1 occurs, what it does, it completes the current instruction that is been, not the current program, current instruction. Okay, so it completes the execution of the current instruction, then the program counter will be having the next address of the next instruction. Okay, so that address is now stored to the stack. Now we have the interrupt enable flags. Okay, so all the status of the interrupt enable flags will be stored to the stack register, and this interrupt is been taken. So this accepting the controller, the indication, the acceptance of the controller or the acknowledgement of the controller to the occurrence of the interrupt is being indicated by disabling that interrupt flag. Okay, and after disabling, the vector address corresponding to this particular interrupt source is been now loaded to the program counter. Okay, so that the controller will be transferring its control to that particular location, and in that location we can have some interrupt service routine. Okay, so normally the sequence of instructions which has to be done or which has to be executed to treat an interrupt may not be fully accommodated in the space allocated, that we'll be seeing when we look to the vector address of the of all the 5 sources. So in that case, once we go to this particular vector address, from there we'll be routing to some other locations so that the enter instructions can be fetched and executing, or the interrupt service routine can be completed. So in that case again, the current location is pushed to the stack and the interrupt service routine has been completed. Now it will be popping the stack, that is it will be coming back to this particular vector address, and there you can see the RATI instruction which indicates that now it's time for the controller to fetch the value from the stack, that is the program counter value which was initially loaded to the stack from the stack address. Okay, so on seeing that, it will be restoring all the interrupt enabled flags, and it will be enabling the interrupt 1 again, because once it has been serviced, now another event can again occur on that particular source. Okay, so it will be enabling that, and now the content from the content to the program counter is being restored from the stack for the next instruction of the main program. Okay, and the controller resumes with the execution of the main program. Okay, so as we told, if we look to the various interrupts that is available in 8051 controller, there are 5 interrupt sources, and based on their priority, so we can see that currently the default priority of the various interrupt sources are starting from highest priority for the external interrupt 0, that is IE0 is a flag corresponding to this particular source. Okay, so this is the bit that which indicates that there is an interrupt from the external interrupt source 0. Then we have the second priority for timer 0, and the corresponding flag to indicate the controller is TF0. Then we have the third priority list priority interrupt resource as external interrupt 1, and the corresponding flag is IE1, then timer 1, TF1, and for UART we have a for reception and transmission we can have some interrupts. So for that we have corresponding to reception, if we need an interrupt, that is indicated by the flag RI, and corresponding to transmission, if we an interrupt has to be indicated, then it is indicated by the flag named as TI. Okay, and if you look to the basic vector addresses, you can see for external interrupt 0 we have the vector address at 0003, and timer 0 has the vector address starting from 00BH. That means there is only a space of 8 bytes between the starting address of the vector spaces or memory spaces of external interrupt 0 and timer 0. So this 8 byte may not be sometimes sufficient to service that particular occurrence of the interrupt. Okay, so in that cases only we will be going to some other location using the jump or call instruction. Okay, as we have seen in the block diagram. Okay, so for external interrupt 0 we have 003, adding 8 we will be getting 00BH for the timer 0. Now adding 8 to this I will be getting 0013H for external interrupt 1, and again adding 8 bytes to this value I will be getting the starting address of the vector of timer 1, that is 001B, and adding again 8 I will be getting the starting address of the vector or I will be getting the vector address starting value of the vector address for serial port as 0023H. Okay, now if you look to the features of the, let's look into the features of the interrupts in 8051. The main feature is that each of these interrupt events that is supported, or the interrupts that is supported by 8051 has to be enabled separately. That is, if I need to enable the interrupt from timer 0, I need to do it separately. If I need to enable the interrupt from timer 1, I need to do it separately. Okay, so for all the 5 I need to perform 5 separate enabling steps. Okay, and each of these interrupt has separate vector address, which we have already seen. And the other feature is that apart from the default priority levels, we can program the or we can modify the priority of each of these interrupt sources by using the bits available in the interrupt priority register. Okay, and we have two external interrupts. So these external interrupts can be triggered either by using an change in the edge level detection. That is, we can trigger those interrupts using an edge level triggered signal or by using a level signal. Okay, that is by a transition from 1 to 0 can initiate an interrupt request, or we can configure such that a logic 0 level or a logic 1 level on this particular pin is going to evoke an interrupt request from the external source. Okay, so that can be configured by the programmer. And the other feature of the interrupts is that even though we are able to it is said that we need to enable each of the interrupts separately, there is a specific provision, or we do have a provision in order to enable and disable all the interrupt sources by using a single bit. Okay, so all this feature, enabling and disabling of all the interrupts and enabling and disabling each of the interrupt sources can be done by using the interrupt enabled register. Okay, so that is what we are told. The separate enabling as well as the whole interrupt system enabling or disabling can be done by using this enabled register. And in order to perform the global enabling of the interrupts, we have the enable all EA bit in the interrupt enabled register. Okay, so if we look to this particular features, it is clear that corresponding to interrupt programming in 8051, we need to have aware about we should be aware about two specific special function registers. One is interrupt priority and other one is interrupt enabled. Okay, so let us look into them. So this is the entire structure of the interrupt. So we have two sources, external sources. As I told, either they can be a level triggered or it can be an edge triggered. Okay, so here you can see, based on this figure, the level 0 on this external pin is only accepted by the controller to indicate or trigger the controller that there is an interrupt. So if there is a logic 1, it won't be treated as an interrupt. Only if there is a logic 0 on this particular pin, then if configured for level triggering, then the controller will be seeing that there is an interrupt from. So okay, if the level 0 is up. Now if you are countering from an edge triggering, if there is a transition from logic 1 to 0 on this particular pin, then the controller or then the controller will be indicated that there is an interrupt from the external source 0. Okay, similarly from external source 1 also we have this particular option. So either of these two options can be selected, and corresponding to that their interrupt flags will be set. Okay, now we have another enabling feature. Only if you are enabling this, it will be further proceeded. That is, only if you are enabling the interrupt from the external interrupt source 0 or enabling the interrupt source from external interrupt 1, then only these flag values will be passed to the OR gate or to the controller. Okay, so that is shown here. So we have two separate switches, which is the bit of 2 of our interrupt enabled register. Similarly for timer 0 and timer 1, so these are the three internal interrupt sources. So timer 0, timer 1 and our UART. So for UART you can have interrupt source either from reception or from transmission, that is RI or TI. So they are ORed and passed to the ES signal. So actually there should be a signal from here to the OR gate. Okay, so these flags will be set on the occurrence of the interrupts. Now if you are enabling these sources using these bits ET0, ET1 or ES, which are available in our interrupt enabled register, they will be passing to this OR gate. Okay, now even though if you are enabling each of these sources separately, if you are not enabling this switch, that is global interrupt enable switch, by enabling the bit EA, then these signals which is coming to the OR gate won't be reaching to the interrupt pin of the uh, controller. So if you look to the basic block diagram of 8051, you can see that we have three interrupt sources from the ROM and two sources from the external, and there is a single arrow mark from the interrupt control block to the microcontroller. Okay, so that is been indicated. That single block diagram or that customized block diagram is been expanded in this particular figure. Okay, so now let's discuss the special function registers required for the interrupt prevention. The first one is interrupt enabled register. So here we can see that it is the 8-bit register, and out of this 8-bit, 2 bits, bit 5 and bit 6 are reserved, and we have the remaining bits. Okay, so by default the value of each of these bits will be 0, and this special function register can be bit addressable. Okay, so here the bit 7 EA should be made 1 in order to enable the entire interrupt. So EA is a global interrupt enabled bit. So making this bit equal to 1 enables the all interrupt sources. Now if I'm making bit 4 equal to 0, then it is ES, that is it enables the interrupt from the serial source. So making bit 7 is equal to 1 enables interrupt from all the sources. Now to enable the specific source of interrupt, I need to make the corresponding bit equal to 1 of this register. Okay, so EX0 is for the external interrupt source, ET0 for timer 0 interrupt, EX1 for external interrupt 1, ET1 for timer 1, and ES for the interrupt from serial. Okay, now this is the priority level, basic priority level. The highest priority goes for the external interrupt 0, then for timer 0, etc. Now if we need to alter this, I can go for this interrupt priority register, that is IP register. Here you can see it is again an 8-bit register, out of which only the lower 5 bits are used. The first bit corresponds to, the D0 bit corresponds to the setting the priority level for external interrupt source 0, then followed by priority level setting priority level for timer 0, then external interrupt source 1, timer 1, and serial 1. Okay, so what is the significance here is that by default we have this particular priority. Okay, now if I make this particular bit equal to 1, it means that out of the entire 5 sources, this is having the highest priority. Always, by default it is always like that, but now I am specifically saying that it is going to have the highest. Now if I am making this equal to 0 and the remaining 4 equal to 1, or if I am making px0 equal to 0 and pt equal to 1, pt0 equal to 1, this means now on execution time the interrupt from timer 0 is going to have the highest priority than the uh, priority of the external interrupt source 0. Okay, so even though by default this is having the first priority, if I'm making this as 1, then it can overshoot the priority level. Okay, simultaneously, so in case if I'm making these two bits together as 1, then it will be following the, so ps0 ps equal to 0, pt1 equal to 0, and px equal to 0, and I'm making px1 and pt0 both is equal to 1. That means that out of the 5 interrupt sources, these two are having the highest priority compared to px0, pt1 and ps. And from these two sources, if both of them executes and or generates an interrupt source at a interrupt request at the same time, then based on the default rule, pt1 will be serviced first, then px1. Okay, only after that the controller will be looking after the interrupt request from px0, pt1 and ps. Okay, only if I'm making this is equal to 1. Okay, so that is the use of interrupt priority register. And there's one more register associated with the interrupt feature, that is timer control register, tcon register. As we told, the lower 4 bits of tcon register are used for the control of the external interrupt source. Okay, so we have IT0 and IE0 and IT1 and IE1. So IE0 and IT1, IT0 are corresponding to the control bits of the external interrupt source 0, and IT1 and IE1 are corresponding to the control bits of the external interrupt source 1. Okay, so what does it means? So if I make the IE1 as 1, it means if making the external interrupt edge flag as 1, IE1 flag as 1, the interrupt source from the external interrupt source 1 will be a waveform of the nature which has a transition from high to low. Okay, that means if I'm making this particular bit IE1 of the tcon register as 1, then only a high to low transition signal, okay, high to low transition signal on the INT1 pin of the microcontroller will be generating an external interrupt request. Okay, then if I'm making the interrupt 1 IT1 as 1, okay, if I'm making this as IT1 as 1, then it will be triggered by this falling edge. Okay, so this is for enabling selecting whether I need to go for a I need to make the interrupt source as a logic 0 level or a high to low signal. So making 1, it sets the interrupt will be activated by a high to low transition signal. If I'm making this is equal to this bit equal to 0, then the IT1 pin will be accepting a logic low level. Okay, there is that, then we doesn't need for a transition from high to low. A logic low level at IT1 will be we can be accepted as a interrupt source. Okay, now to further to control it, if I'm making this equal to 1, so only by making IE1 equal to 1 I cannot enable that particular signal. Only after making these two bits has to be set 1 if I need to trigger the INT1 source by a high to low signal. Okay, so this makes the selection of the signal, and this IT1 is a bit which is going to make the confirmation that okay, a high to low signal which is configured should be treated by the controller as an interrupt signal. Okay, so these two IE1 and IT1 corresponds to the interrupt source 1, and IE0 and IT0 corresponds to interrupt source 0. If IE1 is equal to 1 and IT1 equal to 0, then even though we have set the signal as high to low, the transition of high to low won't be triggering an interrupt request. Rather, after this transition we can see there is a low level, so that low level will be taken as the interrupt will be taken as the source for generating the interrupt request. Okay, so that's the difference. So that's all about the interrupt peripheral or the feature that is available in our 8051. So we have looked into what is meant by interrupt, how the microcontroller acts upon the generation of an interrupt request, Okay, and what are the provisions, features of the various interrupt sources that is available in our 8051, and we are looked into these features of the special function registers, that is interrupt enabled register, IE register, and interrupt priority register, together with the lower 4 bits of the TCON register, which is essential for configuring the external interrupt source and external interrupt generation in 8051 microcontroller. Okay, so in the next class we will be looking upon into the programming of the serial peripheral or the UART peripheral which is available in our microcontroller. Okay, thank you.